Alright, hello and welcome to my three-part series on water vapor equilibrium. Well, I will be discussing the concepts of water vapor equilibrium, obtaining some data, and using Antoine's equation to graph that data in a Python plot. But for this first part, this video, I will be discussing the concept of water vapor equilibrium along with some examples of where you may find this in your own home. So this is a phase diagram of water. It's the relationship of pressure in atmospheres and temperature in Celsius of pure H2O, emphasis on pure. This diagram is only accurate if nothing exists in the space being observed besides pure water, no air. In the bottom section, where water exists as a gas, in the top right as a liquid, and in the top left as a solid. As you can see, there are a few important things labeled here. We can see the normal freezing and boiling points at 1 atmosphere, 0 degrees Celsius and 100 degrees Celsius respectively. So, let's see right here, normal freezing point and normal boiling point. We can see the triple point down here, where all lines separating the phases of water come to one point, and therefore at this point all phases coexist. But what I especially want to point out is more visible on the next slide. So, here's the same diagram in a little bit of simpler terms. We can see the different phases labeled ice water and water vapor, liquid water obviously, and then the lines separating these phases. So I highlighted in red specifically the line separating the gas and liquid phases of water. This is where the water vapor equilibrium can occur. When water molecules are moving from the liquid to the vapor phase and from the vapor to the liquid phase at the same rate, they're in equilibrium. So you can kind of see that in this little diagram right here. All these red dots represent water molecules, and down here we have them a little bit more clustered together because this is a liquid, and then up here they are a little more spread out as a gas. And as it points out, this would be the phase transition across this line, and as long as these molecules are moving into this stage or phase, and then these molecules are moving into this phase at the exact same rate, these would be in equilibrium. And then I also have a little picture right here kind of showing the same thing in a boiling pot with some cute water molecule guys. Alright, so the first and probably most accurate example of this is a pressure cooker, where eventually all air is removed and only water and water vapor remain. The internal pressure rises when heat is applied because the temperature rises, and the water molecules can't escape. Using a pressure cooker is a great way to cook meat because the food retains its moisture and cooks quickly. So, if you can imagine, I've never used one of these, but you've got your water, you've got whatever you're cooking, meat, vegetables, whatever it could be. You seal this thing off, and as the heat is applied and the temperature rises, that water begins to boil, creating the water vapor, steam, whatever you want to call it, and all of the air that was trapped in here, inevitably, with your other things, is eventually removed, and once that's removed, all that remains is your water and water vapor. And so eventually, at a certain temperature and pressure, these will be in equilibrium, and that allows this meat, let's just say we're cooking, a steak or something in there. That allows the steak to retain that moisture, because if you think about it, there's liquid water in there, and in equilibrium, the steam would be entering that meat and being evaporated from it or the water would be being evaporated from it at the same rate. So it allows you to cook things quickly, easily, and retain the moisture. Second example is a boiling pot of water. This is a little bit more familiar, I guess, but it would really only be accurate if we boiled the water until all of the air was expelled and then somehow perfectly sealed the pot with the lid, without any air trapped inside whatsoever. If we were able to do this, the liquid water would be turning into water vapor, and the water vapor would be turning into liquid water at the same rate at the right temperature. But again, this would only completely exemplify the phase diagram if we were to somehow be able to seal this off perfectly with no air, just the water and the water vapor. But as long as it's at the right temperature and pressure, this would eventually hit